Welcome to Module 4. In Module 4, we're going to learn how to test differences between means. And this introductory lecture is meant to give you an overview of the different lectures in this module. There's more of them than we're used to. They're no longer, but there are more of them than we're used to. And then at the end of this lecture, there's a brief kind of conceptual overview of what we're going to be doing during our time together this week. The first lecture in this series will help us understand the different types of tests that we can run when we're testing for mean differences. The second lecture will deal with the null and research hypotheses. I cover these in broad strokes, and then I encourage you to work within the Revel text to practice with some concrete examples. And then the third lecture deals with the sampling distributions of differences between the means. We learned about the sampling distribution in the last module, but this module is directly relevant to what those distributions are for the given techniques that we're learning about. Then the fourth lecture deals with how to find levels of significance. This section in particular is one that you'll need to spend some time within the Revel text on. There are some assessments that are built by the instructor for the course that will be very, very helpful for you as you proceed through learning this complicated material. And then the fifth lecture will deal with how to find the standard error of the difference between the means, and the conceptual continuities between the standard error this week and the standard error last week will be emphasized. Moving on, we'll learn concrete steps to test the differences between the means. As before, there are no formulae in the lectures. The formula exists within the Revel text itself and with the supplementary exercises, and I encourage you to practice those that are available to you. After we learn how to test differences between means, we'll learn how to test dependent samples. Sometimes we test people before and after an intervention, and sometimes we test people that are matched in some way, like twins, for example, or siblings, or roommates, etc. 7.8 will deal with the case of one-tailed tests. Up until this point, we'll have learned how to test for a difference. One-tailed tests allow us to test for an increase or a decrease. And so one-tailed tests are more specific, and they have implications for levels of significance. After we learn about hypothesis testing, we'll learn about presenting effect sizes as complementary information for effect size, as complementary information to the hypothesis test. In the literature, best practices across research and practice all suggest that effect sizes as well as confidence intervals should be reported along with the results of significance testing. So we'll continue with that theme and represent it in our course. And then finally, the last lecture in this series will discuss the requirements for testing the difference between the means. In terms of a broad overview, remember that the primary goal of research is to test hypotheses so that we can correct our false assumptions about data and so that we can figure out what works. And what we want to know is if we observe something different than we would expect, we want to be able to assess and answer the question, is that observed difference beyond what we would expect by chance variation? So when we learned about the sampling distribution, for example, we learned that, let me draw this for you. We learned that as we're making these decisions, we're interested both in what is typical as measured by the mean, and we're also interested in the extent to which observations vary underneath that mean. And so the basic idea, we know that observations are going to vary because there's the existence of the width of the curve. So I know that not every sample that I'm going to obtain, for example, is going to have a mean value exactly equal to this mean. I'm going to have observations over here, and I'm going to have observations over here, and over here, and over here. And the idea is I want to be able to say, what is a likely degree of difference within sampling error? And what I do throughout the course of this chapter, we'll learn, is I set up portions under the curve that correspond to what I'm going to call beyond chance levels, such that if I have an observation of a mean that lies in this area or in this area, I'm going to conclude that those observations are different, are more different than chance variation would assume. I know already that observations are going to vary just due to sampling error. And I can set up a certain percentage underneath the curve for which I expect that to happen. Commonly, this is set at 95%, okay, or 99%. Which is why in the last module we talked about a 95% confidence interval and a 99% confidence interval. I can set up areas of significance that correspond with different areas under the curve. And then if I observe a score within these areas, then I can conclude that my observation, okay, my observed mean, is different beyond that which we would expect by chance. Okay? And the researcher defines that area. So if I have a 95% confidence interval, for example, I'm going to put 2.5% at the top and 2.5% at the bottom. Okay? And then my task is to say, is my observed mean in this area? Okay? And to the extent that it is, then I'm saying that we're concluding beyond chance levels that this is different. So a test statistic is what we're going to call in this chapter a t-ratio. And it represents ratios of observed variability to error variability. The type of test statistic that we're going to discuss depends on the data and on the research question, but they all have in common the fact that the numerator of the ratio is always a mean difference. Either I'm looking at the difference between a sample mean and a population mean, or I'm looking at the difference between two independent means, or I'm looking at two means that are matched in some way. And then the denominator is error variability. So this slide kind of gives you a general overview of the types of things that we're going to be looking at. We're asking questions, is an observed mean significantly different than would be the case if only sampling error were operating? I compute a ratio, okay, a t-ratio, and these t-ratios are plotted along this axis, and I'm looking for them to be in what we're calling here a critical area of rejection. This is a critical area of rejection, and this is a critical area of rejection. If my t-ratio falls within these areas, then I conclude that the difference that I've observed is beyond error variability.